The third talk is by Huijun Lim, who's a final year PhD student at KAIST, advised by Dong-Soo Han. He has worked on improving network systems and machine learning systems through designing efficient algorithms, and will be talking to us about accelerating model training in multi-cluster environments.
Hi, this is Huijun from KAIST. So in this session, I'm going to talk about our system named SIGCOMM'24, which accelerates model training in multi-cluster environment with consumer-grade GPUs. The field of machine learning has shown incredible growth driven by the development of complex models. So since training this model requires massive amount of computing power and memory, distributed training has gained traction. So large companies such as Meta and Microsoft have built massive GPU clusters to train such models. In addition to industry, there has been increasing demand for distributed training in academic environments. However, academic environments typically face stringent budget constraints, so it's common to use consumer-grade GPUs and slower internode connections. However, consumer-grade GPU lacks support for GPU-to-GPU data transfer, so they must rely on slow interconnect to exchange data. Despite the limitation in their moderate performance, this is cost-effective solution for academic environment because this is 10 times cheaper but only 50% slower than data center grade GPUs. However, there are some challenges when you try to scale the distributed training with consumer-grade GPUs with slow internode connects. To scale and accelerate training, researchers may want to augment their resource with remote resources to save costs. So for example, they may want to augment on-premise resource with full resources from collaborators or from clouds. However, this becomes a problem when the WAN bandwidth is insufficient and becomes bottleneck. So where does this bottleneck come from? So let's take a look how the distributed training goes. So after the forward and backward pass, we need to exchange the local gradient in each node to aggregate gradients with all reduced communication. And we need to run a model optimizer to obtain new model version from the aggregate gradients. Here, when the network bandwidth is insufficient, communication becomes a significant bottleneck, stalling the training progress. This leads to a GPU underutilization and increased training times. So how much bandwidth do we need? We measure the model size and batch processing time to find the bandwidth needed to exchange gradient without stalling the training. Here, x-axis shows the model size, and the y-axis shows the batch processing time, and x divided by y is equal to the required bandwidth. The large model would require more bandwidth, and complex model with long batch processing time would require lower bandwidth. However, popular models like ResNet, VIT, or GPT-2 require more than 1 gigabit per second, which are far above the WAN bandwidth between cloud lab clusters. So, to train such models with insufficient bandwidth, we must either accept stalled training or adopt a synchronous approach, which greatly slows the convergence. To address this problem, existing work adopts gradient compression to accelerate training in low bandwidth environment. This selects and exchanges a small fraction of gradient updates. For instance, BytePS compress and HyPress implement efficient GPU-based compression algorithm, and Espresso compare and select optimal compression strategies within data center GPU nodes. However, these are without limitation. Not without limitation. They target a bandwidth of over 25 gigabit per second, a speed that is rarely achievable in multi-cluster settings. Also, technique used to reduce communication overhead between GPU brings additional computational overhead. This leads to a trade-off between network load reduction and computation load. In some cases, time taken for the compression is almost equal to time taken for the forward and backward pass. So the goal of our system named SIGCOMM' is to achieve optimal time to accuracy, or TTA, in a hybrid multi-cluster environment. TTA can be further broken down as the reciprocal of the product of iteration speed and convergence speed. Iteration speed is basically the GPU utilization. It is the throughput of the batch processed by GPU. So this ideally should be bound by the GPU throughput, but this may be bound by the network bandwidth if it is insufficient. And convergence speed is a factor that shows how gradient inaccuracy slows down the model convergence. For example, a synchronous approach can improve the iteration speed, but at the cost of the convergence speed due to high staleness. So balancing these two speeds to optimize TTA is the essence of our design goal. So we explore new strategy and revisit existing solutions to improve TTA. We first explore techniques that optimize training pipeline, which can enhance the iteration speed without affecting the conversion speed. Then we explore strategies to holistically optimize TTA, which affect both iteration and conversion speed. And SIGCOMM' is an optimization framework that directly optimizes TTA. I'll first discuss strategies that optimize the training pipeline. So training models with consumer-grade GPU using existing training pipeline comes with two major problems. First, we cannot pipeline forward and backward paths with the compression, as we cannot run different operations on the GPU at the same time. Second, GPUs need to wait for the communication to be finished before moving on to next iteration. And we also cannot pipeline the optimizer. So this pipeline leaves GPU idle for a large amount of time. Here, there's an opportunity we can leverage. We can better pipeline the training with CPU. As consumer-grade GPU do not support GPU-GPU copy between nodes, so gradient must first copy into CPU RAM for inter-node communication. So this implies that the model's gradient already exists in the CPU RAM, so we expect no additional cost for copying gradient from GPU to CPU. So we can offload tasks such as gradient compression and model optimization to the CPU. This can achieve better pipeline of training tasks and free up the GPU for the forward and backward paths. However, why is the training pipeline still slow? First, CPU-based compression optimizer is much slower than GPU-based one, so this may degrade the benefit of the CPU offloading. So if we can accelerate CPU-based compression optimizers, this will streamline pipelining and make iteration speed much faster. Also, GPUs still need to wait for the gradient exchange with another node, idling the GPUs. So if we can out-of-bound the staleness and allow GPU to process without waiting for the next gradient, we can achieve full utilization of GPUs. So when the GPU is idle, we can embed another forward and backward path iteration in between. And we maintain the bounded staleness of 1. So the gradient from the iteration 1 n would be used for the iteration n plus 2. So SIGCOMM' adopts suggested two approaches and leverage both CPU and GPU to maximize iteration speed and achieve full GPU utilization. So we let GPU to focus on forward and backward paths, and we let CPUs to do gradient compression, optimization, and gradient exchange. So we out-of-bound the staleness and employ two optimization techniques to optimize iteration speed. We will take a look at the two optimization techniques in more detail. So the problem of existing approach is that CPU-based optimizer is slow. Its computing time is significant when compared to the time it takes for a forward and backward pass. Existing naive approach to update the model with sparsified gradient decompress the compressed gradient into a dense matrix and using an ordinary optimizer to update the model. However, this introduced too many computation, increasing the computation time. Here, since only the parameters of gradient exist in the sparsified gradients are updated, so we can reduce the computational burden by selectively updating the parameters using sparsified gradients. We call this sparse optimizer. In action, sparse optimizer effectively reduces the number of computation for the optimization. However, a 99% compression ratio does not directly translate to 99% reduction in optimization time. Actually, it takes 18 times longer time than expected computation reduction. The reason behind this is, with highly sparsified gradient, typically only a single element from each CPU cache line is needed. So this leads to a frequent CPU pipeline stalls and long waits for the DRAM access. So given the limitation of the sparse optimizer, we propose an improvement, a cache-aware version of gradient compression. Instead of simply selecting the top k element, we select the top k divided by cache line size blocks, aligned with cache boundary. This increased the cache ratio and reduced the CPU pipeline stalls. A sparse optimizer is up to 17 times faster with this cache-aware compression. Now I'll discuss strategies for holistic TTA minimization. As we adopt fixed bounded stainless of 1, we explore the space of gradient compression and batch size and evaluate the impact on the iteration and the convergence speed. For these configurations, the impact on TTA is marked as a question mark because if we change this configuration, this would impact the iteration speed and the convergence speed in opposite direction. So we need careful tuning for this. First, when we adapt batch size to achieve optimal TTA, there's a trade-off because the batch size affects both iteration speed and convergence speed. When the batch size is small, we suffer from slow iteration speed since small batch cannot saturate GPU. Also, small batch size incur frequent synchronization, which can cause network bottleneck. However, we have better convergence speed as frequent synchronization provides faster model performance convergence. When the batch size is large, we can achieve high iteration speed since there is more time for the gradient exchange and batch will saturate the GPU. However, we suffer from low convergence speed due to infrequent synchronization, leading to higher staleness in terms of the number of training samples. As in the batch size, there are also similar trade-offs for the compression ratio. When the compression ratio is small, we suffer from slow iteration speed due to high network bottleneck. However, we have better convergence speed coming from higher quality of gradients. In contrast, when the compression ratio is high, we will benefit from faster iteration speed as we will minimize the network overhead. But we suffer from low convergence speed due to low quality of highly sparsified gradients. So to optimize TTA, we must co-optimize both the batch size and the compression ratio by modeling convergence speed and iteration speed. We model the convergence speed as the function of gradient compression ratio and batch size. We need to explore over the large space of gradient compression ratio and batch size, but obtaining a convergence speed for each point requires multiple steps of probe training. So naive method of exhaustively visiting all possible points makes modeling impractically expensive. To model the convergence speed with lower costs, we adopt Bayesian optimization to obtain a surrogate model to estimate convergence speed. Once we are finished with the Bayesian optimization done offline, we can simply query the function to look up the convergence speed. Next, we model the iteration speed. To model the iteration speed, we need to consider computation time and communication time. First, to model the computation time, we model the GPU processing throughput in terms of batch size. When the batch size is smaller than a certain threshold, GPU is not fully utilized and the iteration speed increases as the batch size increases. When the batch size reaches the threshold, the iteration speed gets saturated. And each GPU and model have different batch size that saturate GPUs and different saturation throughput. Second, we consider the communication time. In our pipeline design, the communication time must be no longer than the computation time, or it'll suffer from the training pipeline stall. So to keep communication time within the computation time, we apply the constraint on the gradient compression ratio and per device batch size. These constraints are determined by the environment such as link bandwidth, model size, and iteration speed. Using these two models, we find the best gradient compression ratio and batch size that minimize TTA. To apply this optimization, we implement a centralized controller that collects telemetry from GPUs. First, the controller loads a model profile obtained via offline profiling from the Bayesian optimization. The controller collects the telemetry data from each worker and estimates the performance of each GPU and network bandwidth. And then, controller finds the best configuration parameter for minimizing TTA. And finally, the updated configuration is applied to the worker asynchronously. Now I'll discuss how we evaluate train. We use 3 nodes in on-premises cluster with 2 GPUs each, and 1 node in remote cluster with 4 GPUs. For reproducibility, we use emulated bandwidth between clusters using the network bandwidth trace we measured between 2 cloudlet clusters with average link bandwidth of 150 megabit per second. We show that train is significantly faster than existing compressed and uncompressed systems and achieve up to 104 times faster TTA than PyStore DDP. SAGCOMM' also dynamically adjusts compression rate and batch size based on the bandwidth, achieving higher iteration speed despite the fluctuation on bandwidth. We also show that SAGCOMM' can fine-tune LLM up to 8 times faster than PyTorch TDP, which was evaluated on GPT-2 model. And by leveraging a combination of public cloud and on-premises clusters, SAGCOMM' can reduce cloud code by 64%. Compared to using only 6 on-premise GPU or only 8 cloud GPU, it is much faster and cheaper to utilize both resources powered by SAGCOMM'. This approach can be beneficial for researchers who want to augment computing resource with public cloud resources. To summarize, SAGCOMM' takes a holistic approach to accelerate model training in consumer-grade GPU clusters by co-optimizing several acceleration techniques. SAGCOMM' can accelerate training in multi-cluster settings with limited bandwidth, while also adapting to bandwidth fluctuation. Thank you for listening.
Hello, Menghao Zhang from Beihang University. I have 2 questions for you. First, it seems you only update part of the gradient. Will it impact the model coverage?
So actually, it affects the convergence speed, but it does not affect the final convergence. So it would make the convergence lower, maybe about 20%, but eventually the model will converge to the same accuracy.
Okay, thank you. My second question is, can your approach support tensor parallel? Because tensor parallel need a really large bandwidth.
So actually, this is our first work in our research group, and we only focus on the data parallelism in this time. But this can be extended, like if we can use tensor parallelism inside the node, and if we can, use the data parallelism in the interim node, then we can apply this, use this approach to use the multiple kind of parallelism at the same time.
Okay, thank you.
Okay, thank you for a great talk. This is Jinrong from Duke. So I just have one question. So how do you stably measure time to accuracy? Because the curve, if you look at the curve, like x-axis is time and y-axis is accuracy, if you train twice with some like a random seed, the curve may just be different. And time to a certain accuracy threshold may be different. Like even like if you set accuracy like to 95% and train twice, sometimes the second for the second trial it just never reached the threshold. So how do we stably measure the time to accuracy?
So we actually maintain a certain target for each model to reach certain accuracy, and actually we measure the time to reach a certain accuracy. So yeah, I agree that it may differ from model to model. Yeah, but in our evaluation, we just set a custom target accuracy, target loss, and we just measure the time we reach for the target loss.
Yeah, okay. I mean, if you train twice, the result might be different. It might reach the accuracy threshold earlier or later. So how do we stably measure it?
I just kind of take some, in our evaluation, we just kind of take some, measure the time it takes so we actually count the number of iterations to arrive at a certain accuracy or loss.
Okay.
Yeah.
Okay, sounds good.
Well, let's thank the speaker again.